All right, welcome back to another calculus lecture. In today's lecture, we're going to begin a study which is going to last pretty much this whole week on how the derivative applies to the shape of a graph. So we're going to look at the derivative and use that to determine different features about the shape of a graph. And at the end of the week, we're going to be able to actually give a pretty good picture of the graph of a function without having to use any graphing software whatsoever. Before we get there, though, there are a couple of theorems that I want to talk about concerning differentiable functions. And the first of these, so that's what today's lecture is just a couple of theorems with some nice graphics to go along with them. The first of these theorems is called the mean value theorem. So, mean value theorem. And the mean value theorem says this. So if two things are true, so if f of x is continuous on the closed interval a to b, so I require the graph of f of x to be sort of connected on this whole interval, and I'm going to require it to be differentiable on the open interval, so I don't care about differentiability at the endpoints, but I want it to be differentiable throughout the whole open interval, so it's differentiable on the open interval a to b, then there exists a point C such that, so just a number C, such that A is less than C is less than B, so that is C is in between the two endpoints of the interval that I'm looking at. And the important thing is that f prime of C, so if I evaluate the derivative at that point C, this is equal to f of B minus f of A divided by B minus A. Now, that's all fine and dandy, but what does this actually mean? Well, let's think about this. So if f of x is continuous, so its graph is connected, and it's differentiable, so it's not sort of sharp anywhere, then there's a point C in this interval that I'm looking at such that the derivative is equal to, what is this quantity? This is the slope of the secant line connecting these 2 points, so which is slope of the secant line connecting connecting the points A f of A, so this coordinate pair, and B f of B. Right, if I wanted to compute the slope between these 2 points, this is precisely what I do. So maybe let's take a look graphically at what this represents. So we'll do some fancy-dancy transitions. And so notice what we have here. So my 2 points that I'm interested in, my interval, is going to be the 2 black dots here that the blue line is connecting. So these are, this left point is A, or A f of A, this right point is B f of B, and the secant line connecting them is the blue line. What the mean value theorem says is that there's another point, C, in between A and B, such that when I evaluate the derivative there, that is, if I compute the slope of the tangent line and then construct that tangent line is going to be parallel to the secant line. That's precisely what it means to have the same slope. It just means that your 2 lines are parallel. And so you can see that as I vary my points, my point C changes. The mean value theorem doesn't tell me anything about where this point is located, or even how many points there are. There could be more than one. But as I vary this, you see that I do get at least one point where the slope of the tangent line at that point is equal to the slope of the secant line connecting the 2 points. Okay? And that's all the mean value theorem says. It just says that you get this special point where your derivative is equal to the slope of the secant line. Okay? So let's switch back here. Maybe let's do a quick example about maybe sort of how to reason with the mean value theorem. So example, let's let f of x equal x squared. So let's find the value of c guaranteed by the mean value theorem, or MVT, if a is equal to 1 and b is equal to 4. So what we're going to do is we're going to say, okay, well, the mean value theorem gives me this special point c in between 1 and 4 where the derivative of this function is equal to the slope of the secant line connecting these 2 points. So I want to go ahead and try and find out what that value of c is. So how do we do that? Well, the mean value theorem says that there's a point such that f prime of c is equal to f of b minus f of a divided by b minus a, which in our case is going to be 4 squared minus 1 squared over 4 minus 1. This is going to equal 16 minus 1 is 15 divided by 3, and this is of course just 5. And then what is f prime of c? Well, f prime of c is just 2c, right? I take the derivative of x squared and I get 2x, so this is just going to be 2c. So what are we really interested in? We really want to solve the equation 2c equals 5. Well, that's easy enough. C is just equal to 5 halves. And so the mean value theorem says that we get this point c, and we've done this analysis to show that, okay, this point that the mean value theorem guarantees me is actually just the point 5 halves. And if we go and actually look at a graph of this, the yellow line here is the graph of x squared, and the blue line is the secant line connecting the points 1, 1 and 4, 16. And then the green line here is the the tangent line at the point 5 halves, right in the middle of 2 and 3. And you can see that these lines are in fact parallel. They have the exact same slope. Okay, so that's all the mean value theorem sort of says. I think it can be a little bit sort of confusing when you just read it. It's like, okay, what does that really mean? Well, it's a very simple sort of geometric statement about the existence of certain points. Okay, so the next theorem I want to talk about is an application of the mean value theorem. That is, we can use the mean value theorem to prove this theorem, and we will do it. It's a nice little computation. But before that, we need to introduce a little bit of a definition. So definition a function f of x is increasing on an interval a to b, maybe, if, and increasing is the word we're defining here, if for x1, x2 with x1 less than x2, that is, I'm just going to use 2 points that where one of them is to the left of the other, so x1 is to the left of x2, and they're both in this interval, so x1, x2, these are an element of this little scripty e right here, just as a fancy way of saying both of them belong to this interval, so x1 is greater than a and less than b, and the same thing is true of x2. If this is true, so then f of x1 is less than f of x2. Okay? So what this means is that a function is increasing if, when I move to the right, my function value gets bigger. So the function value on the left is less than the function value on the right. Geometrically, maybe let's go ahead and draw this out. I didn't have a graphic prepared in Mathematica, but we can draw one of these out very quickly. So an increasing function simply looks like this. So if I have x1 and x2, then f of x1 is less than f of x2. That is, it's just below f of x2 on the graph. So as I move to the right, I move up in my function values. Okay, so that's just an analytic way of saying that. Likewise, a decreasing function is defined the same way. So a function is decreasing on a to b if the same assumptions hold but f of x1 is greater than f of x2. That is, as I move to the right, my graph is, get some colors here, my function values are getting smaller. So if this is g of x, this is f of x, so some very quick and dirty graphs. You can see that as I move to the right, as x1 sort of moves to the right into x2, then my function value is getting smaller. My g of x2 is below g of x1. It's just less than that. Okay? So I think rather than memorizing these sort of analytic definitions, just think about what the graphs mean. I think it's fairly obvious from a graph what a decreasing and increasing functions are. So let's go ahead, now that we have this, let's go ahead and state the increasing function theorem. This is the increasing function theorem. So suppose f of x is, and we're going to have the same set of assumptions, continuous on the closed interval a to b and differentiable on the open interval a to b. And so if this is true, then if, and I guess we'll bullet these a little bit differently, it's just a and b. So if f prime of x is greater than 0 on a less than x less than b, so that is for all x in this open interval, then f of x is increasing on a to b. And likewise, if f prime of x is negative, so it's less than 0 on a to b, then f of x is decreasing on a to b. Okay, so what is this theorem saying? It's saying that whether or not my graph is sort of tending upwards or tending downwards is controlled completely by the sign of the derivative. Notice that if I try to construct a tangent line at one of these blue points right here, that tangent line would have a positive slope. And likewise, if I try to construct it at one of these green points, it would have a negative slope. Okay, that's all that this theorem is saying. So you can actually prove this using the mean value theorem. So let's go ahead and do that. So what do we want to show? So we want to show that given 2 points, x1 less than x2 less than or equal to b, if f of x is positive, and we'll just do the increasing one, the decreasing one follows by the same sort of reasoning. If f of x is positive on, or f prime of x is positive on a to b, then, well, I want to show that my function is increasing, so I want to show that f of x2 is greater than f of x1. That is, when I move to the right, when I move from x1 to x2, my function value gets bigger. Okay? So that's my goal. Well, let's maybe rewrite this real quick. So that is f of x2 minus f of x1 is greater than 0. Well, this is already sort of looking like at least the numerator of what the mean value theorem gives me. Notice that if I take this and I divide by the difference between x1 and x2, well, that's a positive number. So this is equivalent to f of x2 minus f of x1 divided by x2 minus x1. That's equivalent to that being greater than 0. So I want to show that this inequality is true, because all I've done here is I've just divided by a positive number on both sides of an inequality, which doesn't alter the inequality at all. Since 0 is on the right, this is certainly true. So I just want to show that this inequality is true. Well, this already looks like something that the mean value theorem considers. So let's try and apply the mean value theorem. So by MVT, there is a point C such that x1 is less than C, which is less than x2, and f prime of C is equal to f of x2 minus f of x1 divided by x2 minus x1. That's precisely what the mean value theorem gives me. Notice we had the two suppositions in our theorem. We had that we were continuous on the closed interval and differentiable on the open interval. And so we can apply the mean value theorem. It's always important to check those. So we have this, this point C where this is true, but what do we know about the derivative? C certainly lives in this bigger interval, a to b, and what do I know? I know my derivative is positive in that interval. So I know that this is greater than 0. Well, that's it. We're done. That's what we wanted to show. Therefore, f of x is increasing on a to b, because I've chosen any two arbitrary points and shown that the derivative, that if the derivative is positive, then the difference between those points, the difference of the function value at those 2 points, is positive. And that's precisely what it means to be an increasing function. Okay, and we're done. That's it. So that's a proof of the increasing function theorem. The main thing to take away from this, so main takeaway, is that increasing is equivalent to having a positive derivative. And likewise, decreasing is the same thing as having a negative derivative. Okay, so that's really all that I wanted to make sure that I covered we're going to look at the shape of a graph more in the next few videos, so I wanted to ensure that we understood that we can determine increasing and decreasing by looking at the sign of the derivative. Okay, so that's it for this video, and I'll see you all in the next one.